We started with density functional theory in our last session. Now we just continue with density functions. But first, let us repeat. We also had in the last session the Hartree-Fock algorithm. Just to keep in mind how it works, we set up all our positions, our basis sets, whatever we have. We compute all the integrals with our basis functions. We determine our density matrix from the expansion coefficients, compute the Fock matrix, diagonalize the Fock matrix so that we get the energy eigenvalue matrix, new coefficients, and as the eigenvectors, update our density matrix, compare if it has converged. If yes, we compute observables. If no, we just repeat until we are self-consistent. Next, the Kohn-Sham equations, right? Our energies, and these are the Kohn-Sham equations. With our functional, this is the function, this is the potential of the nuclei with respect to the electrons. This is our Coulomb potential. This is some exchange and correlation potential. These are again our basis functions. Right, so we have some kind of Hartree-Fock-like approach. And this yields an algorithm which is also looking Hartree-Fock-like, but some details are different. So number one, we just do the same. Where are our nuclei? What is their charges? How many electrons do we have and which bases do we use? Nice. We compute matrix elements, but this time, of course, as we have some of our elements, some of our terms in our Kohn-Sham equations are density dependent, we cannot compute all the terms yet. Right? We can only compute those terms which are not depending on density but directly on the wave function, which is actually the core Hamiltonian and the overlap matrix. And then we determine our density matrix as we did, and the density. Please watch this, the density matrix is not the density. We obtain the density by multiplying our expansion coefficient matrix with the overlap matrix. This is important. Actually, SS doesn't change. We have some kind of bijective mapping, but the density itself is not the density matrix. So then we compute our integrals. This is what we have inside the brackets of our Kohn-Sham equations. To obtain the full Coulomb integral, we also need to integrate the second time, right? First density, second density. Or let's say a slightly shifted subspace and the full space then. Both are going over the entire space. It is just to find out what happens if you vary the electronic density to the Coulomb potential. And our exchange and correlation energy, which is the exchange and correlation functional times the density. Now we have collected all the terms we need, and we can compute the Kohn-Sham Hamiltonian, the full matrix, in terms of our basis functions, right? And from here, well, it looks like Hartree-Fock, doesn't it? Diagonalize, get the energy eigenvalues, get better coefficients, update the density matrix, compare. If converged, get to our observables. If not, go back here. Because it's this, we have a new density, right? We just multiply this with the overlap matrix, have a new density, can compute these integrals anew. And this is a major difference. Now we are not completely in a form which is purely vectorial, right? We have our integrals now all the time again. We do not have such an easy formalism as this Hartree-Fock. And this typically goes on the cost of scaling. So the larger the system gets, the longer it takes. So if Hartree-Fock is scaling with basis functions squared, DFT is typically basis functions cubed. Good thing is when we are working in the condensed phase, that is a plane waves, the scaling is much better. So plane waves approach yields to a much better scaling.
So this algorithm is more specified than the one in the previous slide, right?
Yeah, this is only for density functional theory.
Right, but I'm comparing this one with your previous algorithm, this one,
yes.
Right? Hartree. So this is more general.
In principle, no, this is only valid for Hartree-Fock theory, and the other one is only for density functional theory.
This one only works on wave function, the other one works on densities. Right?
Yes, right.
They're two different methods.
Actually, the other one works on a hybrid of density and wave function.
Right. So through this one, because you are also solving the eigenvalue problem, right?
Right.
So once you get this energy,
is just here.
Where's the difference?
The difference is just in the parts before we get diagonalize, right?
Right.
So just in this little part here.
But if you get this energy, which is the eigenvalues, you can just use this way to get a density function as well, right?
Yes, but this density function is lacking correlation.
Is it less correlated?
Yes. The only correlation we have here is the exchange.
But I thought this one is more general. In other words, well, I don't know the words.
No, it is not. They have the same level of generality.
Well, in terms of the, let me see. So, I guess this one is more accurate compared with the DFT.
Actually not, because it is lacking the correlation.
I thought DFT has
no,
the fundamental assumption.
This one is more accurate from the physics.
This is more accurate.
From the physics.
Yeah, so that's what I'm saying.
Initial, but it is not more accurate, but it is accurate when we assume that there is no correlation except exchange.
What?
The
But
density functionals have correlation beyond exchange, right? Exchange is dynamic correlation, and we also need static correlation. And this we only get with our density functionals.
But then, why are you saying this is more realistic in terms of physics? Because whatever, we are solving the physical problems, right?
Yes.
So whether you use this one or using DFT, my understanding is DFT, as you just mentioned in the other side, with a specific algorithm. I thought that one was more hypothesis based.
Here we can just solve each of our integrals, everything, every term can be solved analytically. But the density functionals themselves are also analytical functions, but they are not analytically derived. So here everything is analytical. The entire derivation of our integrals, everything is analytical. The density functionals are not analytical. They have large analytical parts, but some lacking information is just derived by fitting.
So basically you said that, as far as I remember in the last session, that something went horribly wrong with Hartree-Fock, right, so that we had to do DFT to solve that problem. For example, you brought up the idea of like 2 hydrogen atoms and you wanted to put them far apart, right?
Right.
And you showed that Hartree-Fock cannot capture that problem.
Right. Because Hartree-Fock is lacking the static correlation.
Okay.
Static correlation is not in Hartree-Fock. So this is our algorithm. Now we need density functionals, right? So somehow we need to have this exchange and correlation energy, which we somehow need to derive. So first of all, we need a good model. What is a good model? Well, a good model is when it describes our density accurately, correct?
Yes.
So let us just consider the following. Start with something simple. The electrons are free particles in a box. So it's only limited by the boundaries of this box, which, by the way, can also be periodic, so that in principle we emulate something which is infinite. Now, this yields a uniform and constant density, right? If we do not have any other potential, our density is uniformly and constantly in any portion of space. So wherever we integrate any portion of space, we just get the same value. Because we are free of any external potential, external with respect to the electrons. So a nucleus would already be an external potential. Or electric fields or whatever. So we have absolutely nothing with, well, with one exception, of course, we may get some smaller perturbations, right, of electrons. So some minor fluctuations are there, but if we integrate out time, then we are completely constant. Now we add some nuclei to the model, and to take things easier, let them be distributed homogeneously. Even more, let them be just all of the same kind. Then what our electrons experience is a force from some kind of periodic potential, right? Within a certain arrangement of our nuclei. So it is somewhat three-dimensional cosine or sine potential from the nuclei. They are all just going down, but with a neighbor again, then you're just seeing attraction, repulsion, attraction, repulsion, attraction, repulsion all the time in all three directions. So with this, we get a resulting density of electrons, right? And this resulting density of electrons is no longer constant because we have different areas, attractive and repulsive areas. But we are still homogeneous. So now we can look how can we solve this. Actually, this can already be done almost classically from electrodynamics, or more accurately from quantum electrodynamics. And this yields a solution, very nice, very analytic, for the exchange part. Actually, this has been derived by Wigner in 1923, long before density functional theory came up. As an approximation to Hartree-Fock theory, one might say. Also, this is even a little older than Hartree-Fock. We also get a kinetic energy part for this, which all works pretty fine. So we have a nice analytic form for exchange. Which is good news. We're analytic in the exchange. But we just have the exchange at this moment, right? So something is still missing. Because when we're just using exchange, we could just have stayed with Hartree-Fock. Hartree-Fock yields exact exchange. So we didn't gain anything. But, of course, there's still correlation left. But we do not know an analytic expression for correlation energy, at least not an expression which is analytic all the time. What you can derive from quantum electrodynamics are two limits, a low density limit and a high density limit. Low density limit means, or let's start with high density limit, right? High density means many, many electrons in a single place. So close to a nucleus, for example. Low density is, well, just the opposite, right? If low density goes to the maximum limit, then we have a density of 0. Or we have anything in between. So low density can be van der Waals, low density can be a hydrogen bond, it can also be a big bond. So we know about limits. For the low density case, we know that we can just write this expansion with the Thales radius, which itself depends on the density. So this is easy. And for the high density limit, we obtain this nice equation with 4 parameters, which are, by the way, also all density dependent. But it's the same analytical form, so they're depending also on RS and the density. So it's pretty nice. We know what happens at high density, we know what happens at low density. And we have no clue what happens in between. So if you have a true high density case, works fine. If you have a true low density case, works also fine. If we have any other case, which typically is the reality we are facing, it goes wrong. But we can still work. I mean, we had a series expansion, right, for the low density case. So we can just use this expansion and set some boundaries. First thing is minimum density is 0. Next thing is maximum density is 1, and when we have 1, we have the high density case. So we have some boundaries. There are many solutions. One thing we can always do is to apply the variational principle. If we would know our exact exchange and correlation energy, we can vary with respect to density, and we can obtain this. Some kind of offset and some kind of derivatives. Nice to know. Also, we can just say exchange correlation energy is actually exchange energy plus correlation energy. The exchange we know exact, right? If we can find any way to measure this, we take this measurement and this term we can compute, and what remains is the correlation energy. Nice stuff. Actually, it's looking much worse than this when we're going. So, one thing we have to face is that we have two different spins, alpha spin and beta spin. And it's not necessary that we have exactly the same amount of alpha and beta. So we have this spin factor, which is then alpha minus beta divided by alpha plus beta. Well, what's the purpose of this? If the spin factor is 0, we are fully diamagnetic. Same amount of alpha, same amount of beta, just yields a 0. If we are plus or minus 1, we have all spins in the same direction. We are fully paramagnetic. This gives us some nice boundaries. This has an influence on spin density, and spin density has an influence on electronic density. Sure, all with the same spin doesn't like to stay at one place. So with this factor and the Thales radius, which is density dependent, we can get something like the full diamagnetic case. We have the full paramagnetic case. We have the difference between both of them. And then we have here some kind of switching factor and switching function. And this function itself also depends on the spin density.
One question.
Yes.
How do you get the constants in these? Good question.
Well, these guys actually performed a lot of Monte Carlo simulations. And then they were fitting
Monte Carlo simulation of what?
on electronic densities.
So basically full electronic, not DFT, right?
Full electronic, full Monte Carlo, so that the density was
What method
very-
did they use for calculating the full thing?
Actually, they were just using variations of energy with respect to density from the Kohn-Sham equations.
So they were still using Kohn-Sham.
Yes,
To fit-
but they did
To
not.
fit a parameter in Kohn-Sham? It sounds weird.
But they did not. Well, actually, not directly Kohn-Sham. Sorry, my mistake. They did not use orbitals.
Yeah.
They worked only with the density.
Yeah.
So they were using the kinetic energy expression from the free electron gas. The Coulomb is directly computable. It's whatever you have, you just need the density. And then the exchange part is exactly known.
Yeah.
And so they just varied the correlation parts. And
Such
until
that the
they-
energy minimized,
Yes,
right?
right.
Oh.
For many, many systems, and then they fitted to all of these systems.
Oh.
Actually, for many, many metals. Because this is a theory which works properly for metals. Because this is just the model, right? The same kind of very homogeneous distribution of nuclei, homogeneous even in the charges, and the electrons are free. This is a conductor. They can move wherever they want, they're not really localized. And with this, we obtain these nice, well, the equation is analytically derived still, but the parameters themselves are fitted, which is in our case only the alpha parameter. Right? This is the only variable parameter which we
Yeah,
have,
sure.
alpha.
Can we use it in a system that is an alloy, for example, gold and silver, or is it just a pure metal?
Actually, this is for pure metal, but it still works for alloys. Interestingly.
But not for ceramics.
For ceramics, it starts to work a little weird.
What do you do here? On physical
Some
results or?
some strange behavior when it comes to, for example, to the bands. So the band gap is too low, often, not always, or too high, can also happen. And especially when you have something like a defect, then it already is, it doesn't take a defect so easy, not in the metal, and even worse in ceramics.
So it depends on what you want to calculate. If it is band gap, it's not accurate. But maybe if I'm measuring, for example, lattice parameter, it might.
It might still work, yes. So for just ground state properties, it still should work. Unless your system gets too heterogeneous. So if you, for example, have something like you mix calcium oxide and silicon oxide and aluminum oxide together, perhaps add some iron oxide to it, then it will go horribly wrong. Because then you have so many different localizations that it cannot capture.
Thanks.
But this can. Because when we're getting heterogeneous, right, we're getting the wrong behavior from the LDA. Sometimes, by the way, this before, the local density approximation, the LDA is also sometimes called LSDA, which means then local spin density approximation, but it is just the same method, so there's no difference. Yeah, and then we have the GGA. So, problem is that the gradient of the density influences the exact correlation at inhomogeneity. So when we are becoming inhomogeneous, then close to the inhomogeneity, the gradient is important, the steepness of our density as a function. matters. And it matters a lot. So what we can do is we just correct our LDA. Exchanges should be independent of the gradient. So we just need to correct the correlation principle with some gradient depending term, which is just like we have here our uniform electron gas correlation, and then we add such a gradient depending part with T is not exactly the gradient, but gradient with some spin factor. Kf is the Fermi gap. This is important. If the Fermi gap is getting 0, we're in a metal, and then this anti-equation is just no longer valid, so that this anti-correction is just no longer valid. Well, actually, we can overcome this so that we do not face a big problem.
By Fermi gap, you mean the wave number at Fermi level, or?
Yeah. So if we don't have a Fermi gap, if the levels are just matching, then, well, we don't need a gradient. Sure, we're in a metal. LDA is valid, right? So, problem is, this correction also influences exchange. Because the gradient is not independent of the density itself. And so we also have to correct our exchange function a little bit. So in principle it's independent, but because we correct the correlation, we have to correct our exchange as well. It's like you're driving and you're finding out that the car isn't, that the street is not so perfect. You're correcting in one direction, but a little bit too much. You find out, okay, that's also not good. And you're just going back a little bit. So this is a little bit problematic, but it works. And finally, we can do more. So we have good functionals in principle. Right? We can work with heterogeneous systems, we can work with homogeneous systems, we have everything we need. But we also know that Hartree-Fock theory yields our exact exchange. Regardless of the system, Hartree-Fock is always exact. Unlike the DFT exchange functionals, it is directly derived from our basis functions and not from the density. So we avoid any errors we make in our density. So why don't we reduce our Cohen-Sham exchange a little bit and add a little bit of Hartree-Fock? If we interchange by 100%, it would not work, because then the correlation functional would be missing its counterpart, the exchange function. But we can add at least a little bit. Many exist of these kinds. The PBE functional, which is, by the way, just this one here, PBE. Can be augmented with some Hartree-Fock. So we reduce our PBE exchange by a quarter and add a quarter of Hartree-Fock. Very simple.
And is that ratio arbitrary, or that's the best ratio?
Is the golden number? Or
They
that's
had the idea
yeah,
that this
right.
might be a good idea, so that they also tried some different ones, but this one was the best matching. At least when you want, as long as you want such a simple approach.
So it doesn't have any mathematical derivation, right? It's, they just try this
Works
stuff.
well with
This works
experiments.
best, right?
Yes, just works best. You compare with experiments and then we look and see. Yeah, gives the best results.
So it's some sort of a fitting again.
Yes, it's a fitting, but in this time they are typically you're optimizing molecular structures then, and look at the bond lengths where you fit best, or cell parameters, anything like this. By the way, this is a pretty good functional, despite the fact that it's so simple. More widely used functionals is, for example, the B3lib. And, okay, I didn't display the second one, the HSE06, but it doesn't matter. This is probably the most famous of all hybrid functionals. It's used almost everywhere, and especially wherever you're dealing with organic chemistry. So, what do we have? We have exact LVA exchange and correlation. The correlation is this BWN formula. Actually, there are 5 BWN formulas in the paper of these 3 guys. Number 1 is crap, number 2 is crap, number 3 to 5 are okay. Number 4 is a little bit complicated to compute. So you can use number 3 or number 5. Then you have such a factor, and here you're just looking for Hartree-Fock exchange minus exact exchange. So you just correct your exact, your LDA exchange, right? So we take a factor where we correct a little bit. And then we add this delta means gradient. In this case, these are both gradient corrected functionals. So this is just a gradient correction from a specific functional, B88, which you then add. So actually this reduces your exchange. With this you correct back again, but with a gradient correction. So we have LBA exchange corrected by Hartree-Fock, corrected by gradient correction. And then we have the Li-Yang-Park correlation functional, which is also a gradient corrected functional. And with this we will correct the correlation of LDA. Works pretty fine. These parameters are fitted, and they are working just fine for organic molecules, even for organic crystals. So you already get some idea on how these exchange correlation functionals are made of, right? Like you can combine almost any exchange functional with almost any correlation functional, but you need to have the correct factors. Because some exchange functionals already include a little correlation by the way they were derived. It's just an accidental correlation which is in. And some correlation functionals include some exchange, which is also just accidental from the fitting. So what we get now is some exact exchange. Nice stuff. We can even get exact correlation. So here we need correlated electronic structure methods. Of those, one is the simples, and this is second order perturbation theory. Simples in terms of computer cost. We do not want to have much computational effort, right? And second order perturbation theory is giving us just this. So we have DFT exchange corrected by Hartree-Fock exchange. We have DFT correlation corrected by perturbational correlation. One example is the B2P lip. So this has Li-Yang-Park correlation. It has Becke exchange, and P is for perturbation. What we see here is we have gradient We have here GGA exchange energy, which is an LDA plus gradient correction, right? Add some Hartree-Fock exchange. Add this gradient corrected correlation, and add some perturbational correlation energy. And this perturbation term is pretty nice, because once we have our Hartree-Fock orbitals, we just need them. So we take these two electron integrals, Coulomb minus exchange. You remember this shortcut for this integral, right? Occupied and unoccupied. This is important, because the static correlation is mostly a multi-determinant correlation. So what if? Anybody watched this video on YouTube MJ sent you the link for, about quantum mechanics? Yeah, because there you know that you have a superposition of all possibilities. The ground state is the most probable one, but the others are still there. And they are influencing the ground state properties to a certain degree. So this is in principle the mathematical way of describing this. And then of course we need the difference between the orbitals, occupied, unoccupied. This is a scaling. The more they are away energetically, the lower is the perturbation. If they are in direct contact, the perturbation is 100%, which is probably not good. Because then it's not a perturbation, it's a significant part of the system. But typically they are like 10% at maximum. So this is nice. And we already have it from our Hartree-Fock. We do not need to solve any integral. It's all in the Hartree-Fock. These are from our eigenvalues, these are from our 2-electron matrices. So we can just recycle what we already have. And we need the Hartree-Fock because otherwise we wouldn't get this part. So it's all in there. Still has a bad scaling. This now scales with an order of 4. Because we still need to compute this sum. That's a double sum, and it takes time. So this is the most accurate we can get with the density functional, these double hybrid functionals. By the way, as we come from perturbation theory, this also includes van der Waals automatically from this part. Actually, we are adding just that much van der Waals as our factors here, but it includes van der Waals directly. Because it has a full long-range behavior of correlation. And this is what we need for van der Waals.
It's super expensive.
Yes, it's much easier to use other approaches for van der Waals correction.
In theory it's nice, but in practice,
You don't want to do this with a solid.
yeah.
Not for
But
van der
when you
Waals.
have like water molecules, right, or ions
Yes.
moving in a lattice, right, and when van der Waals interactions become dominant, then you want
Well, typically this function is used for gas phase calculations. There it works fine. In the bulk as well, but it's a difference if you have tens of atoms or hundreds or even thousands, especially with the scaling.
But again, the parameters C, B, A,
All
X
fitted to a training set.
to a training
If you are not confident with your results, make your own training set. Fit the parameters.
That's a little bit of a stretch, right?
In principle, you can fit very specific.
But they have done this fitting For what kind of materials? For they had a database of all
They had a
the
database of especially lots of weakly bound molecular species.
organic,
reaction-
inorganic, or was mostly organic?
Also inorganic. So there they had small clusters, typically with ceramics. They didn't do much fitting to metals with this, because this perturbation term is not very grateful for being close between occupied and unoccupied. But in principle, it works just fine for almost any system, which is interesting because they started from a B3 lib, which is more or less completely fitted to organic stuff. And now they have something, just by adding some correlation correction, you're also good with inorganic materials. Funny thing. Tells us a little bit of about the electronic structure of inorganic materials, doesn't it?
So, in choosing our exchange correlation functional, we should see what is our system and what we want to calculate.
Yes.
Based on that, we should choose the problem.
Right. So, next, final thing, pseudopotentials. So, we are going for materials chemistry. This means that we are probably most times in the bulk or with a slab, but at least we are periodic. We are dealing with solids or liquids. So, we want to fit some kind of Slater type orbitals still at each of our atomic centers, right? Wherever an atom is, there must be something Slater-like. But if you want to construct something in the plane wave spaces, we have our cutoff of the plane waves. So here we have this cusp. We can go up to the maximum, but typically we do not need that much. We are working here, right? We're doing the chemistry, we are not interested in what happens in the core shell of the electron. They just influence everything around. For sure they do. Without this repulsion would be lacking, right? So they're somehow repulsing the valence electrons and make sure that they stay in the right distance, but that's all that happens here. So how can we avoid this? Very pretty simple. We just need to tell the electrons that there is no space for them. So we just take some potential here, which we then multiply, in principle it's just added to our electronic wave function. So wherever our plane waves are coming, as soon as they are coming here, they are just reduced so that they are zero in the nucleus or close to it, and they are still fitting the valence part. And you see how nice you can reduce your plane waves cutoff. Yes?
So the x-axis is the position of the nucleus.
Right.
And
This is the amplitude of the wave function. So we put a negative amplitude to the wave function, wherever it is here. In this way, we avoid the singularity at the top of the Slater. Right? It should end in the singularity. We do not have this. Typically, we are using Gaussians for this. So we have an analytic solution to all our integrals. And as we know what is the width of our core shell, we can just make sure that our pseudopotential covers this correctly. This also means that we do not have to describe our core shell electrons. They are out of our calculation. And think of this, you have these electrons how can we take something as simple as oxygen, right? Oxygen has 8 electrons, but 2 of them in the core shell. So, in principle, Actually, 4 of them are in the core shell because the 2s is also part of the core shell. So half of these electrons don't do anything. So what does it mean? Make a pseudopotential, but all of a sudden it's only half the integrals. We can even do this with a Gaussian type basis set, no problem. But especially with the plane waves, it works fine. The fun of the plane waves basis is that we do not scale with the number of electrons, but with the cutoff.
So,
At least for the density. Yeah.
so for this thing, we have to know the width of this Gaussian, right? And
Yes.
so the width of Gaussian determines, I mean, like which electrons are you on.
Yes.
And
Right.
should we guess that in our calculation?
No,
or the
the
other?
pseudopotentials which are published have been computed, all with an accurate, with a proper DFT functional each, in a Gaussian basis, so that you directly can measure the width of your core shell. So they are all functional dependent. Do not use a pseudopotential which has been optimized for PBE for BLIP. You can be lucky and it, by fortune, just has exactly the same core shell, but if not, then the electrons in the valence shell do not experience the correct repulsion. And then all of a sudden, all of your bonds are either too short or too long, and you wonder why your cell is just lacking the accuracy anywhere, right? So people publish with PBE, I get an accuracy of 1%, and you're just, why do I only have 10? That's the reason. So make sure that you are always using the right pseudopotential.
What do you mean by cutoff?
Cutoff, you have your cutoff energy, right, in Rydberg's.
In the
Normally in any kind of energy unit, you have your cutoff energy when you are selecting how many plane waves are there. You do not say I want 2,000 plane waves, you say I have a cutoff there. Each plane wave has its own eigenvalue and they are filled up until they are above this, right?
okay, so it means, for example, if my basis set has, for example, 100 plane wave equations,
Yes.
then each one has different energy.
Right.
So when I say, for example, the cutoff is, for example, 20 Hartree, it means take the plane waves that their energy is less than 20.
Yes, all the plane waves which yield a kinetic energy for the electrons which is below 20 Hartree is then taken for each atom, right? So, well, they're not really centered, but you just take them for all the atoms. So in principle, you have a degeneracy with the number of atoms. So, and if the kinetic energy is not sufficient to yield these, because the closer they are getting to the core, the higher is their kinetic energy. So in principle, this form, this exponential form, is not only the density, but also the kinetic energy. You can map them.
So take the electrons with this amount of kinetic energy and put them in the pseudopotential.
Yes.
Yeah.
Yeah, so everything that's above is just, yeah, considered okay. This is just a potential. Actually, it's these electrons are just visible by their mean field, electric mean field to all the other electrons. Right? So the pseudopotential is just yielding some kind of mean field. But with a nice mathematical way, by just putting electronic density to 0 or reducing it. So, and the last thing, convergence, I already told you. So you know, when is our cutoff sufficiently high, right? When are we converged? Well, first of all, it is very important to have this for accurate calculations. because otherwise, if you're not converged, then the funny thing is, when your basis is not converged and you say the SCF should be accurate to a microhartree, the SCF will be accurate within a microhartree when it's finished. But your energy is not. Because your basis is not converged. It is only accurate within the basis. Any kind of SCF, any kind, be it DFT, be it Hartree-Fock, is just as accurate as your basis allows it to be. You can still converge to very low deviation within this basis because it's a variational principle. It varies until it reaches the maximum it can get for this basis. But this does not mean that you're converged in the energy. Fun thing is, you do not need to have more than a single geometry for your system to check the convergence. It doesn't even have to be converged geometrically, right? So you don't even need a minimum or a transition state or whatever. You just take one more or less reasonable geometry for your system. It just needs to include all the atomic kinds you have in your system. You don't even need to take the same system. So if you want an alloy of iron, manganese, and chromium, you just mix something with iron, manganese, and chromium, put it there, and then look for the conversions. Even if all your bond lengths are too short or too long, it will give you the correct.
Even the chemistry is not important?
No, for this the chemistry is not important. Well, for the SCF it may be important because when you're in a so wrong geometry that you're getting far too high correlations, then it may happen that your SCF itself doesn't converge.
But it doesn't matter if I'm testing it on, for example, steel with 5% carbon or 2% carbon.
No,
I can use the same.
right. You just need to include carbon to the steel. Yeah. So, and then you can convert. Pretty simple. Here you see it's a cutoff, energy, and the total energy. The absolute values of the total energy are not important. Because what you're looking for is differences. How much does the energy change if I change my cutoff? You see, when you're far off from a converged basis, you see a large change. But it's an exponential decay. So in principle, you can extrapolate. You don't even need to run all the, just extrapolate. Of course, you can also say, oh, I want to be sure, and then I just say cutoff of 300 Rydbergs. But this is not good because think of it, you're working with 300 Rydbergs. This yields a lot of basis functions. And then you're working with a K space, perhaps. So you're meshing, which just means you're just projecting them into several images, which is still multiplying them even further. And then you have your typical matrices, which are of dimension like basis function times basis function. And then all of a sudden the software tells you, give me more memory and I can do it. So it's okay to do this if you have infinite memory and infinite CPUs, but it's not okay for practical application. You see, it converges pretty fast. Right? And these computations itself, they don't take so long.
Just a single point.
Yeah, single point doesn't cost much time. Right.
But the system is so big that you have
Yes, but that's why you do this once in the beginning to obtain a good value here, and then you can use this value for all subsequent calculations on the system. You want to get the stress tensor? Okay, but you already have the right one. And it is important to have it, to think of it, what is the accuracy of the energy you really want? This is very important and you should make up your mind for this. And when you have this, you just converge to this point, no more. Keep the basis as small as possible and as accurate as necessary. So this, I have tested it with a system of around about 350 atoms, and it took like one single point. But of course, the computer time is getting up with this, but in the end, it was still just a matter of several minutes on 8 CPU cores. So this is something one should always have. So it's an hour of work, and it can save you either big embarrassment by reviewers in a journal, or a horribly too large basis. And both is something you don't want to have.
You can run them at the same time. You write a batch file, run 6 of them at the same time in a few minutes.
Right. Then
You have all of them.
Then it's so you start it before you go to lunch. You return. You look at it, and you know where you are. It's worth. It's really worth the effort, right?
You should do it. It's mandatory.
Because normally you don't work for one single system for just a day. You want to know a lot about this system and similar systems, and as long as you're similar, as long as it's the same atomic species, it is fine. You don't need to do the work over and over again. You have it once, and you know it. You know when I have these species, that's a cutoff. Pretty simple. Which, by the way, leads me to the exercises. So, on the HPC cluster, you have a module which you can just add. This yields all the settings for quantum espresso what you need. Okay, so you don't need to look what compiler settings or whatever. No, this is already with all the settings. Look at the home page of the OIT, right? Here they describe how to make a batch script, how it works. You also get some information on how this cluster works, so that you can set up everything correctly. You will need norm-conserving pseudopotentials. You can get them here. I have just prepared this. Is it the right one? Yeah. So, this is a web page for pseudopotentials, and here you find such a nice periodic table. So you're taking your functional, whatever it is, right? So let's say I take, let's go for the TPSS, right? You may look for a specific pseudopotential library, or you just take any. Here's the type. Can be a simple Coulomb potential, so it looks like a Coulomb potential, but of course it is not Coulomb. So it's just 1 by R with some factor. Norm cons are norm-conserving pseudopotentials, plain augmented wave, and ultra soft. Normally the norm cons are working pretty fine, and for beginners I think they are also the easiest to deal with. And then you can have other options, so scalar relativistic or not, full relativistic, and so on. Typically you don't need to select one, and then let's see, you just click here on iron. So this gives us severals, right? Okay, I think I've just selected you, doesn't matter. Or, no, here are all of them. So, you see, for what potential? So, they are fitted for BLIP, and here you get more information. That's just the method, that's a functional exchange correlation, not just volume. Here it is for the valence, right? It is non-relativistic, so we cannot non-relativistic start with that. Okay, classification unverified. Well, it's an open source project, so the programmers do not have time to verify each single of these pseudopotentials, but they are from literature, so they should work. You find them all in the literature. Here you find the next one, and so on. Here's PVE. If you find something with FHI, you can in principle trust it. That's from Fritz Haber Institute, which is a Max Planck Institute in Berlin, so these guys know what they are doing. And you see it's from the Epinet website, so it should work. If it works with Epinet, it works with other similar stuff as well. Here. So then you just select whatever one you want. That's it. And then all you need to do is mark all, copy, paste. That's it. And name this file properly so that you will find it later on, of course. But that's in principle it. Copy, paste into the file whatever you want, and it's working. And then, I can just show you. You have the convention input anyway, but I can just show you how it works. So, anyway. So it's looking like this, okay? You have for everything, I've entered your command. So that you do not need to look it up in the manual. So here's everything you have. Okay, it's actually just a one line. Let me look at it, but that's how it looks. You can also open this. I have this file prepared. I think you loaded it up. So you can just open this with any text editor, look for it, see what's inside. So it should run. There are some things which are important, title and so on not. Okay, one thing here is iGraph. Set the Bravik grid to 0, which means no symmetry. This enforces you to later have the cell parameters defined as Cartesian vectors. But when you do a calculation with symmetry, then the software will do symmetry operations for you. So this means you reduce your cutoff in principle because it's not necessary. When you have a high symmetry, it's just automatically added by the symmetry operations and so on. And when you have symmetry defined, your initial guess wave functions will be symmetry adapted. And they stay symmetry adapted for the entire computation. So if your system changes chemically, by temperature, whatever, it will still keep the symmetry. So whatever kind of optimization of property, whatever you do, I can only recommend to go for it without symmetry. Perhaps when you want to optimize a cell and you know it has a specific symmetry, in the end you can go for it.
It's only correct for the local minima that you are
Right.
If you change the pressure, you want to see any sort of a phase change, right?
As soon
This
as
is gonna break it
as
down.
soon as you're getting off the local minimum, the symmetry will break, but you do not allow it to break if you don't have a symmetry of 0. Only a symmetry of 0 allows this. And then you have things like number of atoms. This one is also important. you do not need to use this. Typically it is just 4 times this value. This is the per atom value, this is the density value. This works as some kind of auxiliary basis to directly compute the density integrals without the need of the contributions of kinetic energy at the atoms. It is nice. It can be different to this, to 4 times this. It can be lower, it can be higher. You can adjust a little with it, but typically you do not need to do anything about it. So just keep it 4 times the amount of this one, just the default value, or just comment it out with an exclamation mark in front of it. You automatically comment this line out, and then it will run easily. Yeah, far down you will get all your atoms, everything. These are the names for the pseudopotential files. And before that, somewhere in the beginning, you define a directory where to look these files up. Make sure that it is your home directory or wherever you store them. Otherwise, the software won't find it and it will crash with did not find pseudopotentials. Okay? And then the K points. When we are working on a gamma point, we replace automatic with gamma, right? When it is gamma, this line is not read. It's not necessary, because it will just be 0, 0, 0, 0, 0, 0. Doesn't matter. With automatic, you need to enter some values here. And this is what I mean with the cell parameters. This is an orthogonal cell, 16 angstroms in each direction. You get, then of course, A is 1600 then in the projection, 0, 16, 0, 0, 0, 0, which is easy. As soon as you have angles, you need to apply some trigonometry to it.
How many of you have seen fractional coordinates before? You're not new to that. So you have to study a little bit how to go from Cartesian coordinate to the fractional coordinate. Fractional coordinate is the coordinate that crystallographers work with, right?
Yeah.
So the numbers are between 0 and 1. So you have to take that.
Well, not necessarily. You can
Yeah.
also just specify here everything in your Cartesian coordinates. Make sure that you have, when you have angstroms here, that you have angstroms there as well.
Yeah.
If you have Bohrs in one and angstroms in the other one, you will have a nice surprise. Then you can, whatever you define here, you can also use fractional coordinates on top. This is no problem. Yeah, the other stuff we don't need, and I have the link for the manual added in the end of this example file. So that you just have this nice manual for quantum espresso, and here you find everything, right? Here's every keyword. You see there are much more than in the example file. You can in principle also, if you do not want to go for these vectors, you can define them also in the system part with A, B, C, and the 3 cosines. Or you just have cell dimension equals, and then you have your matrix A, B, C, and the 3 cosines. Also works. So it depends what you prefer. And you need to make up your mind if you want to be in fractional coordinates or in Cartesian. The good thing with fractional coordinates is that whenever you change your cell, the coordinates change automatically. When you're in Cartesian coordinates, you need to recompute them manually first and then enter them. And this can get a little messy. When you're a good programmer, then you can just write some software for you to make these input files, and it doesn't matter if you're in fractional or not, then the software will do everything for you. But normally, it's nicer to work in the fractional ones. I have it in Cartesian now, Cartesian and angstroms, but you can easily change it. Just works the same. With the exception that then you have numbers between 0 and 1 for each direction.
Just go to the Wikipedia and search for fractional coordinate or fractional to Cartesian coordinate. The formulas are up there.
One thing, if you define this here, either with cell dimension or with these ABC and the 3 cosines, do not define them later on in the cell parameters section in Cartesian, because then the software will crash. You cannot do both. You cannot say, this is my cell, oh, and by the way, these are the cell vectors. It will compute the cell vectors itself. If you give both, it crashes. Yeah. So, these are all the sources which you need. I think I have all the links either in the example file or in the slides, so you should find all the links. And then you can play a little bit. Good. Don't be frustrated when your first job goes wrong. Probably then you made a mistake.
If you made a simulation and the first time it worked out, there is something strange going on. Thanks, Andreas.